Good afternoon. Thank you very much for the invitation. It's a pleasure to be here. I know you were DG for a long time because working in the same field. I think first we had a lengthy discussion in Langkawi, Malaysia, Asian Solid-State Ionics Conference. And I used to come to SECRI conference CEST. So we had a long relationship, knowing each other. And then she also had I had the opportunity to have her in my lab for a short time, 3 months or 6 months, 4 months. So anyway, I'm happy to be here. This is an important topic for India. So a path towards sustainable supply chain free electrical energy storage. First, I'm in 2 departments. I'm a chemist, not engineer, but I'm in engineering school. That means we don't do chemistry for the sake of doing chemistry. We do chemistry so that it can be useful to the society. That's why I'm in the engineering school. And we are funded heavily by the US Department of Energy and other funding agencies. And I'm very grateful to a lot of people who have worked with me over the years, including your DG. So I'll have that slide at the end. So now you're all very familiar with this. Energy use is skyrocketing as we go forward, but the use is largely based on petroleum-based fuel. That has a couple of challenges. First, it may not be available forever. And second, pollution. It creates air pollution, climate change, either flood or fire or drought, health hazards, a lot of challenges. So that's what is driving the clean energy technology. If you look at here, China and India have similar population. We are above China in terms of number of people. China right now uses 24% of the global energy consumption. And we are using here, I mean India, okay? Even though in US, when I say we, I mean India, so keep that in mind. So we use here only 6%. So that means if we catch up with China, we will need at least 4 times more energy. US population is 1/4 of the population of China and India, and US is already using 16%. So if we catch up with the US population basis, then we will need an order of magnitude 10, 12 times more energy. India needs more energy than what we use now. Lifestyle is continuously going, multiple cars in the family. In the olden days, we used to have nothing, maybe bicycle or even nothing. So things are changing, more and more industry, air condition, every house is air conditioned, everything costs energy, so that's the way it is going. So we can't think, okay, it's okay, no. You will need more and more and more energy as we are moving forward. So the only solution for India is renewable energy, solar and wind. And fortunately, we have plenty of solar and wind energy. Solar cells are cheap now, not a problem. But the problem is, solar energy is there in the daytime, there is cloudy day, sunny day, wind wants to come and wind wants to come. So how do we collect the electricity from solar energy and wind energy? Store that economically and use it economically. That's where battery comes into picture. There are few options to store electricity and use it. Some of them are location dependent, like hydro, but there is nothing to beat batteries as far as storing the electricity with much more efficient, in a much more efficient manner and use it. But batteries don't come without challenges. All these need to be taken care of. In addition to that, transportation. There is no control. Cars are on the road. It's polluting everywhere. So for cars, batteries are the only viable option, at least now, unless we can make, for example, fuel cells much more cost effective. That may be very challenging for a number of years to come. So there is nothing to replace the internal combustion engine other than using batteries. This is an interesting thing. Smalley Institute, Rice University. Smalley worked on buckyballs. He also got Nobel Prize. So it is from that institute. You see here, what are the top 10 things the humanity is facing the next 50 years? Energy is on the top. And water is as important as energy, as you know. And then food, then you see a lot of things here. This, for me, is a very interesting sequence. If you have problem, then it's all chain reaction. If you have problem somewhere in the beginning, poverty will of course be there, then people will become restless, terrorism, war, disease will be there, education will be lost, democracy will be lost, people will die, or more people may be coming, we don't know, it can mean one of those. You know, energy is on the top. That is the most critical challenge we will be facing as we move forward in the 21st century. Now, those of you who are not familiar with the battery, it looks simple when we use the cell phone and laptop, but it is very, very complicated to get everything you need. Actually, we don't get everything we need. We are barely making it, lucking out. That's all happening. So in a battery, you will have a negative electrode that is called anode. You have a positive electrode that is called cathode. So I will make it as educational as possible. I know you are all not working on batteries. So ideally, these two materials should have two kinds of conductivity. The working ion here is lithium going back and forth. So it should allow, both of them should allow good lithium diffusion or good lithium ion conductivity or sodium ion conductivity for the sodium ion batteries. You should also have good electronic conductivity, because when you charge, right now we are going to charge, you see here electron comes that way, lithium goes inside internally. So it should also support good electronic mobility or electronic conductivity. So your electrode should be a mixed conductor, electronic conductivity and working ion conductivity. That's a requirement. The electrolyte should conduct only the ion, it should not conduct any electricity. If it is, then all the electricity will go inside, heat will go up, you will blow up, safety problem. So that has to be electrically insulator, ionically conducting. This should be both electrically and ionically conducting. Okay, that's fine. I can go to the chemical cabinet, pick up a couple of things, put it in the furnace, cook or something, and then assemble battery. That's not going to work that way. A lot of things we need to consider. We have to now consider energy. We all know physics, chemistry, chemicals are reacting, so we have to consider their energy levels. This is cathode energy level, this is anode energy level. And there is in between the electrolyte sitting here, that also has its own energy level. This is highest occupied molecular orbital, that is lowest unoccupied molecular orbital. So these two energies, the electrode energies, have to be within that band gap. Let's consider a hypothetical situation. Let's assume that this HOMO is above this cathode level, somewhere here. If it is during charge, let me wait 1 second. This is discharge, let me wait. Okay, now I am going to charge. I am removing electron from this and I am putting it over there. If this is above this, instead of taking electron from here, I will be taking electron from here, because I am supposed to remove electron from the highest occupied level. Right now, this is the highest occupied level, but this guy is sitting somewhere here, I will be removing from here, so your electrolyte will undergo oxidation. It is donating electron. If it is, then it will leak the electricity inside, so that cannot happen, it will also degrade. Same way, if that is above this LUMO, when I put this electron, I will put it into the electrolyte rather than here. The electrolyte will be reduced. So right now, all the batteries we have, we cannot operate lithium-ion batteries more than 4.3 volt. You see here, user time, energy density, cell voltage. So if I increase the cell voltage, I can use my cell phone longer after I charge it between charges. Right now, that's limited by this guy sitting here. We have cathodes, which have energy levels here, but you cannot use them because of this limiting factor. So what is so fancy about lithium-ion batteries? The second factor here, amount of charge stored, that is how much lithium ion or sodium ion can store in this material per unit volume or per unit weight. Those are the two things determine how long you can use your laptop before you have to charge it. But that's all related to the chemistry of the materials. Now, the olden days, we still have lead acid battery, every car has it. You see here, they are all having lower energy density, shorter user time between charges than lithium ion, because they use water-based electrolyte, aqueous electrolyte, sulfuric acid, lead acid, or potassium hydroxide in nickel cadmium batteries, and things like that. In that, this window is small. So that means my voltage I cannot get more than 2 volt. Lithium ion, I have 4 volt. All of this aqueous 2 volt, that means I am cutting down the energy density by 2, just based on that alone. For lithium ion, so they have to use non-aqueous electrolytes, water-free electrolytes. So when you think of batteries, we have to consider at least 6 parameters. You can read them. They are all linked to severe material challenges. Their energy level, how the structure is, how the diffusion, how the mobility of electron is, how the mobility of lithium is, are they going to have surface reactivity with the electrolyte, and all those very complicated. Among them, as we move forward, cost, sustainability, and supply chain. This is going to be the dominant factor without compromising the safety. You can't have all great battery, then have one outside the building, then catches fire. We can't have that. Catching fire on the road, we can't have that. So that's what we need to take care of. Now, thinking of cost, it is not raw material cost, everything contributes. If the battery is safe, I do not have to worry about lawsuits, so that saves me money. If it is, I can use it for longer, I do not have to replace it. If it is giving more energy, I can make less number of cells. So everything is contributing cost. Safety, again materials, how batteries manage, battery management system, how the cell is designed, how do I use it? Do I abuse it or use it in a normal way? All of them contribute. Now in a battery, 75% of the cost is coming from the material we use in them. In that 75%, 50% is coming from the cathode, positive electrode. Why? They all have metal ions, lithium cobalt oxide, lithium nickel oxide, or lithium iron phosphate, things like that. So cathode is the most expensive. We started commercialization in 1991 by using lithium cobalt oxide, the red thing. That has to go away because very expensive. Now we are hanging with nickel. Eventually that has to also go away. So we have to be working with things like iron, manganese, sulfur, silicon, and things like that. So that's the future. It may mean like 3 things, but it is all only one thing. What do I mean by supply chain? We have to make a lot of batteries in India. I should have easily accessibility to lithium. We don't want another country to blackmail us. Then the whole business will shut down. Economy will go south. National security will be affected. There could be geopolitical tensions. So all those things will happen. When you want to make battery, you also need a lot of other things, separator, current collector, electrolyte. So how do we create a supply chain situation in the country? How do we produce? Not only cathode and anode, but how do we get all these together? So that needs a lot of thinking, lot of investment, lot of entrepreneurship, everything should happen. So it comes into picture. In my talk, sustainability, cost, supply chain, I'm specifically going to, but I told you, supply chain means it covers everything. In my talk, I'm specifically going to focus on how do we go from here to here so that we do not have supply chain problem or sustainability problem with those electrode materials particularly. So that's what electrolyte, solid electrolyte, if you use that also, you don't want to have supply chain problem. Now it's also, there will be physics people, chemistry here. What all we have is just basic chemistry and physics. That's what it gave to us. Students may think I have to do engineering so that I get a job. Yes. But chemistry is still important, physics is still important. You cannot just remove away and suddenly walk into the lab or company and just do engineering. I used to work with John Goodenough. He's a physicist. I'm a chemist. He will always say, if we know either good physics or good chemistry, we can do good engineering. That is the mentality, and it is true. I believe in it. Everything I learned was chemistry, but we do a lot of engineering. So, how did it happen? These are the three people who got the Nobel Prize. The very first lithium-ion battery was demonstrated in 1976 by having lithium metal as the negative electrode and titanium sulfide as the positive electrode. That had two problems. One, the sulfur 3p band lies at a higher energy, therefore you could never lower this below this. So the voltage is limited to 2 volt or less than 2.5 volt. The other thing is it uses lithium metal. Actually, this was demonstrated in 1976. There were cells in the market, but then they were in the 1980s, they were catching fire, then they have to shut down, abandon. That's what was happening. That's the first problem. Voltage also I mentioned, two problems. Goodenough started his career in 1952 after World War II. He's a physicist. He didn't know anything about electrochemistry. He didn't know anything about batteries. He was doing all magnetic materials. His job was at Lincoln Lab as a group leader to make soft magnetic materials. Some of you know spinel structure, all ferrimagnetic materials. That's what they were doing to get the square hysteresis loop. So he was very familiar with all these oxides. Then 1976, he went to the University of Oxford in England. Then he knew this was done. Okay, they have a problem. Anyway, I know something. I will take these oxides, layered oxides, lithium cobalt oxide, lithium nickel oxide. They already have lithium. I can also get higher voltage because oxygen 2p. He never wrote all these. I wrote it in this paper. By the way, this is an open access journal. You put this title, it will show up. Very good article. It's now 5 years. Already 2,600 citation. I don't know who cites it. Like 400, 500 people are citing that paper. If you want to know more about how all cathode business happened, that's a good one. And I'm also going to write another one. Some of them you will hear in my talk. Don't find time. So there will be another journal article either in JAGS or in the journal. Anyway. So that changed. So because this is at a lower energy, you suddenly have access to higher oxidation states like cobalt 3 plus 4 plus or nickel 3 plus 4 plus. Cobalt 3 plus 4 plus, you cannot have access in a sulfide. You can never, because as the oxidation state increases, the energy level will keep on going down. Remember XPS, you know. XPS we do, binding energy will increase with increasing oxidation state. That means with increasing oxidation state, the energy level is lower. So it's the same thing. That's why I say chemistry and physics are inseparable. People may use different language. They will say Fermi energy, I will say redox energy, right? There are some differences, but approximately, crudely, they're all connected. Anyway, so that gave us, that is what we use now. This was done in 1980 and 4 volt. So energy is doubled. No safety problem because there is no free lithium. Now, this is again very interesting. I mentioned to you in the battery, 50% of the material cost is from cathode. That's why all companies are scratching their head. How do we get even 1 more milliamp hour per gram of charge stored? These are the 3 things developed. Very interesting. They were not developed by students. 3 visiting scientists from 3 different parts of the world. So it is an international affair, but everything happened at Oxford. Mishishima, Japan. He was employed at Tokyo University. He came as a visiting scientist / postdoc, like your DG came to me. Not exactly like a postdoc, visiting scientist, same way. They did lithium cobalt oxide. They didn't think that anybody will use it. Oxford did not want to patent it. So they went to another external agency, they patented it. And then good enough sold this, they sold this patent to 5,000 British pounds to Japanese. You hear me? 5,000 British pounds to Japanese. Good enough get zero. He never got any money out of that. And how much money Japan made? Billions of dollars. I'm talking about portable devices in the 90s, right? Then he left. Michael Thackeray came from South Africa. This is Japan. That's a South Africa. He did lithium manganese oxide spinel. Then he left. I did my PhD here in IIT Madras. Then I couldn't go to US as a postdoc. Although somebody offered me a postdoc, I went south, taught in a small university. Many of the things I'm doing today was what I was doing as a teacher when I was teaching master level chemistry students. I thought my career is over. For my PhD thesis, Professor Goodenough was the examiner. When you do PhD in India, one of them have to be outside. So he was my PhD examiner. So when I was working in Polyanion, Madurai Kamaraj University PG Extension Center, I applied to him. He was kind enough. He remembered my molybdenum oxide PhD thesis. And I didn't know anything about batteries. I mean, I knew electrochemistry is something. Physical chemistry teachers taught that. That's a different electrochemistry than what we use here. So I was able to go 1985. This November, I'll be completing 40 years, leaving the country. So we were there 1 year, 10 months. Then he said, I was on leave. He said, I'm going to go to the University of Texas at Austin. What do you want to do? You want to come with me or want to go back? I said, I'll think about it and tell you. I really did not think about it. I did not ask my wife. They were all in, my daughter and wife in India. I will come with you. Okay, let's go. So that changed completely my career. So I'm very grateful for the opportunity I had to work with him. He's a physicist. He loves chemistry people. So together we were able to do a lot of things. Anyway, so I went there. They already had cobalt oxide. They already had manganese oxide. There was no iron-containing cathode material. How come? Iron is the cheapest material, cheapest element. Why it is not? I told you my PhD dissertation was molybdenum oxides. I will take 6 plus molybdenum oxides, reduce in hydrogen to get 4 plus molybdenum oxides, ternary oxides, not binary. Then I will do a lot of X-ray structure, electrical properties, magnetic properties. That's all I did. Then I thought, okay, why is this not happening? They said iron oxide doesn't work. Okay, what do I do? I'm very familiar with all these molybdenum. You may wonder, battery electrode has to be lighter in weight. How come this guy used molybdenum and tungsten? Because it came from the PhD work I did, very fond of number 42 in the periodic table, element number. So started working on this structure. Okay, it has holes, maybe it will conduct lithium, Fe2, MOO43. We did chemical lithium insertion extraction, published 1987. I'll go to the next slide. 3 volt. If you take iron oxide, iron 2 plus 3 plus coupled, it is less than 2.5 volt. You go same iron 2 plus 3 plus coupled, voltage is increased. How come? Okay, maybe something different structure. Then molybdenum is heavy, tungsten is heavy. Why don't I do with sulfur? Sulfate, because sulfur also 6 plus. This is also 6 plus, exactly identical structure you see here, the Nassigon structure. Suddenly 3.6. Oh man, something else is happening. That is purely chemical bonding. I will explain to you. In this case, each ion is bonded to oxygen everywhere. So this bond, ion-oxygen bond, has certain degree of covalency, depending upon the electronegativity. Here in this structure, the oxygen is bonded to either molybdenum, tungsten, or sulfur, one side, then it is also bonded to iron. This bond, molybdenum oxygen or tungsten oxygen bond, more covalent, very strong tetrahedral groups, very strong covalency. Because it is covalent, highly covalent, this bond, that makes this bond less covalent. The chemistry people sitting here, You all know bonding, molecular orbital, bonding and anti-bonding. Because this is more ionic, the anti-bonding level and bonding level, they are not separated much, because the stronger the interaction, covalent interaction, the greater will be the bonding and anti-bonding level will be split, right? Weaker and weaker covalent interaction, it will be down. So that's why this is higher voltage. Here, sulfur-oxygen bond is even much more covalent than molybdenum oxygen. See how chemistry, simple chemistry. Did I know this before I did the experiment? No. I want a structure where it can go in and out. But it's fascinating chemistry. 3.6. Aha, something happened. That is what is called inductive effect. Then I became faculty. As soon as I became faculty, my department chairman called me to his office. Very interesting. He said, Ram, they call me as Ram because they cannot say Armugam. By the way, my name is Mantiram. My father's name is Armugam. So we all do expand initial. So they call me Ram, R-A-M. Good, nice name. And my department chairman tells me, Ram, we know you are a good guy, but if you work with John good enough, you will not get tenure. Okay, got the message. So if you go and look at my website, I did not have any publication with John Goodenough for 20 years. Only towards the end, 1 or 2 we heard. Completely stopped. So he worked with these students because he was very fond of this. 10 years later, lithium iron phosphate came. But the concept was already here, same concept, inductive effect, lithium iron phosphate, that's the cathode India has to use. Cheap, abundant, no supply chain problem for the cathode. So that came out of this. And this family is also very broad: lithium iron phosphate, lithium vanadium phosphate, lithium sodium vanadium phosphate, fluor. 1/3 of the market in 2022 is by this, but now everything, including US, wants to use iron base. So that work I did gave two things. One, it offered a way to use iron. Iron cannot use in oxide. Number two, it also opened up this whole broad family. Number three, these are the materials good have good safety. What's the safety? Medium. This is the best because the oxygen is very strongly bound, sulfate or phosphate. It cannot lose oxygen, highly stable. Lot of good things with this kind of materials, a very broad family. I'm happy with what we did, and I'm also happy that it is going to be useful. The concept developed was the one which gave the following materials, and particularly for India. It's good. I will also tell something else. India is going to use this. The following people who involved with this work, they were also Indians. There was a student, phosphate, I already did. Then I became busy. I gave to a student, Keeta Aguja. She is from Punjab. That work was not published. It was in the dissertation. Then two other people, Akshaya Badi, Nanjundasamy, they worked on the phosphate. Then they got the LFP. You are familiar with this. So I was the first one who created the concept, and the student did the phosphate. They did the LFP. They are all Indian origin. So we should be very proud. And everybody wants to use this polyanion cathode. Your DG knows very well. And those of you working on battery, you know, there's only one thing. Because of iron abundant, no supply chain problem. Everywhere it is available. That's the only reason. And I'm glad whatever we did in the olden days helps. Now, this is where supply chain issue comes. Cost, this is going to be the most important factor, cost. So here, cobalt is the most expensive. You saw that in the previous plot. Can we eliminate cobalt? Yes. The elimination business, my talk is focused that way. I wanted to do the initial part very clearly so that it is not boring, some kind of a story. Next, eliminating cobalt and nickel, that's where polyanion comes into picture. Lithium iron phosphate or lithium vanadium phosphate or lithium iron manganese phosphate. Next is, can we eliminate lithium? Yes, sodium ion batteries without any cobalt, a little bit of nickel, or if you do polyanion, there is no nickel and cobalt, no transition metal at all, that is lithium-sulfur. This is my dream technology, no mined metal. You don't mine anything, you don't dig anything. Sodium is plenty in the ocean, India does not have a problem. You can also think of sodium-based organic or ecosystems. So from left to right, portables are here, electric vehicles are somewhere here, grid storage is here. For grid storage, the battery has to be very, very cheap. So we may not be able to use the same technology I'm using in my cell phone. Here, cell phone uses a lithium cobalt oxide. Nobody is going to use that for car and certainly not for solar wind energy storage. So that's from left to right, portable to grid storage. And these can be done with liquid electrolyte, solid state cells, not here, but redox flow here as well. So it's a very common. So this is my vision in my group, roadmap. And research is happening in all of this. And obviously I do not have time to talk about everything, but at least you know what we are doing. And I'm again I tell you, I was the first one to show way to use iron. Even those days when I didn't know anything about sustainability, already did that. So it's very strong here. So that's what we are trying to do in my lab. Now with that, elimination of cobalt. So I have some slides. When your DG tells me, I'll stop, but I'll give you some idea because it may be more deeper, which some of you may get bored. So elimination of cobalt. So we use a cathode called NMC. The question is, why nickel, why manganese, why cobalt? Why do you make a salt solution? Why can't you use N alone or M alone or C alone, right? And by the way, I'm going to tell you some things here. Only I write like that. Even two distinguished people, one of them was in the conference. They wanted my slide. So I'm going to publish this, another paper, not this. There are a few things coming along. So there are three important criteria they have to be taken care of, and each one of them act differently for that. Too bad, unfortunately. Let's see here. I had 3 slides, and this is a concluding slide for those 3 slides. I didn't want to have too many slides, so I've deleted 3 slides this morning. So I have this. 2 factors are important. Physics people here, you will appreciate. Chemistry people here, you will appreciate. Inorganic chemistry people are here. Crystal field splitting and all those. First, the cobalt 3+, 4+ band overlaps with the top of the oxygen 2p band. So if I charge that material more than 50%, if I remove more than 50% lithium, I will be removing electron from the oxygen 2p band, oxide 2p band. If I do that, I am introducing holes into the oxygen 2p band. That means I am oxidizing oxide ion to peroxide, superoxide, and oxygen. So it will evolve gas, safety problem. I cannot use lithium cobalt oxide more than 50% of its capacity. Capacity is limited. I call it as chemical instability. If I take manganese well above the oxygen 2p, I have all kinds of manganese 4+ oxide, Mn, alpha, beta, gamma, epsilon, lambda, so many things are there, no problem. Nickel, barely touching. It's in between. That's the point number 1. For that, manganese is good, cobalt is not good. Chemical instability. The next factor is structural instability. This has a layered structure. This is the transition metal ion layer. This is the lithium layer. If I charge it, I remove a lot of lithium from that layer. No positive charge here. There is a negatively charged oxygen. Negatively charged oxygen. They don't like each other. So what will happen? To have chemical balance, this ion will tend to go from this layer to this layer. So charge can be redistributed. When it goes, it cannot directly jump from that 6-fold octahedral coordination to this 6-fold octahedral coordination. The barrier is too huge. So the path is from that octahedral site to a neighboring tetrahedral site to this octahedral site. That's the path. For that, this is my own contribution. Nobody ever did. This is what comes from my teaching. I was teaching 4 years. All this coordination chemistry and crystal field. So, you know crystal field splitting, when we have free ion, all 5d orbitals will be similar energy. The 5d orbitals have different orientation. 3 of them have their lobes in between the axis. The other 2 have lobes along the axis. So when you have negatively charged ligands, oxide or even water coordinated, they will perturb these orbitals differently. So they are split. 3 of them are down. The ones go along in between the axis. Once they are along the axis, it's up. That's called crystal field splitting. electron will distribute here and there. So based on that, you can calculate what is the crystal field stabilization energy. For example, if you have 3 electrons, I will have 1 here, 1 here, 1 here. But if it is splitting, then those 3 electrons will be at a lower energy. So the system gains more stability. So that is what is called crystal field stabilization energy in the octahedral side. Tetrahedral splitting will be exactly opposite. By the way, I teach this in 2 classes, that is 2-3 hours. Now I'm here doing 3 minutes. I'm sorry, but at least you know what's coming. You can read any inorganic chemistry. Hughie book is the best. So that is tetrahedral crystal field stabilization energy. That is that. And if I take this difference, you see, get a quantity that tells me to what extent these ions prefer octahedral coordination versus tetrahedral coordination. You see here cobalt 3+, huge, large negative. That means that's much more stable in octahedral side. So that guy loves octahedral side. Cobalt hates tetrahedral side. It doesn't want to move from that layer to this layer. So that I would call it as a gift. You hear me? That's a gift. That's why that was commercialized first. So that means it does not go from layered structure to spinel-like structure quickly. Manganese, if you take, very small. So as soon as you charge, manganese tends to go from here to the tetrahedral side to here. It goes from layer to spinel. That causes voltage decay. Car companies cannot fix. Madam knows lithium-rich layered oxides. They have broken their head for 10 years. Nobody knew what it is. Oh, manganese dissolves. Yeah, manganese dissolves. Yes. But voltage decay, that's coming from here. You see, very simple chemistry. So that's the point number 2. How it is? Cobalt is good for that. Manganese is bad for that. Exactly, too bad, diametrically opposite. Third, any time you have electronic configuration, 1 electron in the EG band or 3 electrons in the EG band, it will have something called Jahn-Teller distortion. Physics people know that. That means instead of being cubic symmetry, then you will have like this. If you have 1 electron here, if it goes from cubic to tetragonal, that 1 electron can sit at a lower energy, so it will automatically tend to go from cubic to tetragonal. I call it as electronically driven lattice instability. That's what is driving here. If it is, anytime you have that, these ions will tend to charge order, meaning 1 manganese will tend to go to 4+, therefore you won't have any electron here at all. The other one will become 2+, that means you will have 1 electron here, another electron here, no tendency to distort. Manganese 4+ will not have a tendency to distort to tetragonal geometry. Manganese 2+ will not have a tendency to distort. Manganese 3+, 1 electron, if it distorts, it will occupy a lower energy, so it will undergo. So that I call it a charge ordering. Once it is, the manganese 2+ oxygen bond is more ionic compared to manganese 4+ oxygen bond. I can explain more if you need, but we don't have time, okay? Because it's more ionic, that oxygen is more basic, proton comes, trace amount of water present in the electrolyte, ppm levels of proton, attack, manganese dissolves. So that's the problem. So that also we can understand. You see here iron, I told very early. Oh, iron doesn't work in layered oxide, give up and keep going. Nobody ever explained why it is. You see here, iron is high spin, 3 electron here, 2 electron here. Crystal field stabilization in the octahedral side, stabilization energy will be 0. If it is 0, iron 3+ has equal stability in the tetrahedral side and octahedral side. Very easily moving from that to here, worse than manganese 3+. So that's why we do not have any iron containing layered oxide. In the case of sodium, sodium is big, it doesn't want to form spinel, so we are able to use iron in the layered oxide for sodium ion batteries. So we can understand all those. There are few other criteria, you can also see that here. In all of them, nickel is in between, that's why all the action is on nickel. You take any company, Tesla, Samsung, LG, everybody wants to increase the nickel content. Now with the nickel, 3 problems. 1, when you increase nickel, you get higher capacity, but it fades. Cyclability is poor. My battery doesn't work long. That's cycle instability. I also have the thermal stability decrease. That means it loses oxygen at a lower temperature, safety problem. Third, nickel 3 plus is not very stable in air. Lithium comes out to the surface. It forms lithium hydroxide, lithium carbonate. That is called residual lithium. That's basic. If it is, when they make electrode, there will be a lot of clogging. They cannot make good electrode. Headache. This number has to be less than 2000 parts per million. So these three problems. Is it strange? To me, it's not strange. If you take manganese, all these oxides are known. MnO, Mn3O4, Mn2O3, MnO2, no problem. So I know manganese 3 plus is stable. Manganese 4 plus is also stable. If you take cobalt, we have COO, CO3O4, CO2O3, there is no COO2. Okay, reasonable. Nickel, we have only NiO. There is no Ni2O3, there is no Ni3O4, there is no NiO2. That already tells me nickel 3 plus is not stable. That's why you have this residual lithium. So you can understand all these from very basic things. So we make all our materials in our lab. Sometimes I was in Calcutta many times. Can I make nano materials, all these layered oxides, I can use it? Nano is a bad word for battery community. You have to use nano only if something is not working. Lithium iron phosphate, if it is not nano, it won't work because it's the worst insulator, worst ionic conductor. You have to make it nano and coat with carbon to overcome that challenge. Silicon, big volume change, you cannot use bigger particle, you have to use nano. If you use the ones I am talking about, layered oxide, nano, you have huge surface area, huge reactivity, side reaction with the electrolyte. There will be a lot of something called solid electrolyte interface layer. It will not work, so they have to be made. 12 micron secondary particle or 10 micron like you see here. My lab, academic labs cannot do this. I had fortunately some good students. We can make tens of kilograms in my lab, any material, any doping, and that's what we use. The thing I want to show here is all of them have, excepting this, 90% nickel. This one does not have any cobalt at all. NMA, 90% nickel, 5% manganese, 5% aluminum. That cycles full cell, 1000 cycles, graphite anode, pouch cell, cycles as good as any cobalt containing material. So in my opinion, cobalt is not necessary in the layered oxide. Of course, you have to do co-precipitation properly. So I have a startup in Houston. They are working on making these cobalt-free cathodes. So cobalt eliminated. Surface stability is the major problem. Same composition in one case, everything was co-precipitated, so aluminum is distributed bulk and surface. Here aluminum was added after co-precipitating this and heated, only one heating step, but you add aluminum oxide without co-precipitating, you see that is surface, aluminum is on the surface, that cycle is much better than this. So that tells me surface stability is much more important than phase transformation happening, volume changes. This is thermal stability. So we have done lot of doping, so we have a good understanding of which doping, which substitution, which ion substitution, what each one of them do for cyclability, for thermal stability, for safety, for residual lithium, lot of things. This paper is about to come out soon, anytime. So that has 500 differential scanning calorimeter, lot of materials made in our lab, DSC plots. And then we also did synchrotron radiation. So you see here, these numbers are state of charge. At a critical value, the peak becomes very short. That's where oxygen is released, and that number increases when you dope with aluminum or magnesium or boron compared to here. So that gives better thermal stability or better safety, because aluminum oxygen bond, magnesium oxygen bond is much more stable. Boron oxide is on the surface. Surface reactivity is decreased. That's why they have better stability. We have also done synchrotron radiation. The way they lose oxygen is they form two spinel, Li-Ni2O4 first and then Ni3O4. The thermal runaway safety thing happens when it forms this spinel, and that is this. And there is a good correlation between the thermal runaway temperature and frequency in the Raman spectroscopy. So if you do not have a DSC, if you want to do, if you have a good Raman spectrometer, you can put it in the Raman spectrometer, you get the frequency, then you have an idea of thermal runaway temperature is higher or lower. So it's good. Fast charge. We all want to charge in 10 minutes, 15 minutes. So this is electrolyte. Everything is same. 3C charge, 4C charge. You see, NMC 811, 80% nickel, 3000 cycle. Amazing. Graphite anode. This is a cell, 1 amp hour cell we purchased, dry cell. We added this electrolyte and the electrolyte developed by us. You want to know more? It's here in this paper. This is a cell made in our lab, similar. The electrolyte plays a much more dominant role for fast charge and cyclability, for everything. Electrolyte is a forgotten thing. We thought, yeah, it's a little thing sitting there transporting ion, but it is not. The electrolyte is the much more damaging. If you have good electrolyte, bad cathode can be made, bad anode can be made, work better if you have good electrolyte. Now elimination of cobalt and nickel. This is a lithium iron phosphate and lithium manganese iron phosphate. This has to be nano, otherwise it will not work. And then the problem here is, this is already a low density system, crystallographic density. On top of it, you make it nano, lot of porosity. So the volumetric capacity goes down. For all application, volumetric capacity, volumetric energy density is much more important than gravimetric energy density. For car, space is more critical for them. Yeah, weight is important, but not too much worried. But this system is pretty bad for volumetric energy density because nano, porous. This is even worse. When you have manganese, poor manganese redox kinetics, that can also undergo Yanterlar activity, then it can release dissolution. So we have done, everybody does, either hydrothermal or some other ball milling or something. We have developed a precursor by understanding. The problem I showed you here, that is because manganese and iron have to be intimately bonded at the atomic level, molecular level. If it is, then you will have less problem. So for that, what we do? We make a spinel first by high temperature. Take manganese oxide, iron oxide, heat it, you have a good spinel where manganese and iron bonded to next to each other. Good salt solution, no problem. Then you treat with a phosphoric acid or ammonium hydrogen phosphate, lithium carbonate, then you get the material. That material is amazingly dense. This is the layered oxide curve. This is their voltage profile in case you want. You look at here. The material by that spinel precursor, we can calendar up to 2.61. Nobody. This is LMFP. I was in the conference. I won't say which company presented. They said, we want to achieve 2.5 gram per centimeter cube. We already have here 2.61. The material made by other method, we cannot go more than 2.15 because the electrode cracks. So basic chemistry you can use to make the material, and this is also easy to make. So we can go up in volumetric energy density, volumetric capacity, volumetric energy density, and if you look at here, this precursor, lower volumetric energy density, the precursor we use this much. So press density is more important. India wants to make it, that's what they want to use it. They're finally recognizing. Whenever I came to India, I always said use LFP. There is somebody here, that person said, oh, China is not going to NMC. This is 10 years back. Why should we do this? Just forget about what this guy says. Now, suddenly, every company in India wants to use LFP and LMFP. So. Okay, there is another one to reduce the cost further. You can take a cobalt-free layered oxide like I talked about, like this. Then you blend that with this. One good, beautiful thing I like is this voltage profile. This is layered oxide LMFP blend 70-30. The voltage profile looks more or less similar to the layered oxide. Not exactly, very nice plot. This can again give better, this blend can give better cyclability, better safety, also lower the cost, as you see here. So a lot of advantages. This is not too many people working on it. We have already a paper published. And we are doing a lot of work with this, lot of different combinations. This is also valuable for India because when you blend it, you decrease the total amount of nickel in the cathode because you have another component there that is also contributing to the energy density. Finally, elimination of lithium. That is sodium ion batteries. We think lithium is replaced, sodium is great, but sodium has a lot of other issues we need to tackle. It looks like sodium ion batteries evolve a little bit more gas, and hard carbon evolves hydrogen gas. So all these things need to be worked out. And also, we cannot use graphite. Hard carbon is another animal. We need to completely understand, very dependent on who made it, how it was made, biomass use, whatever use. We think biomass is cheap, it's there, just burn it to get it. Yes, but it won't work properly. It may give a lot of gas or it may not cycle. There are so many things we need to worry about. So don't think it's ready to go. No, more things we have to learn. We have to be realistic. So there are three possibilities: layered oxide or Prussian blue that can have safety because temperature is increased. You can have hydrogen cyanide evolved or cyanogen. Cyanogen is worse than hydrogen cyanide. It can kill people. So it's very hard safety-wise. The polyanion for this has lower energy density, so layered oxide may be the best. So what can we do? Electrolyte again plays a big role. This is localized high concentration electrolyte, only one solvent, trimethyl phosphate solvent. Sodium nitrate is the solid diluent. That's a new concept compared to other electrolyte. That cycle much better. It also is non-flammable. This is our electrolyte. You see, it doesn't catch fire. The other two catch fire. And less crack on the cathode with that electrolyte. No dendrite on the anode. More inorganic derived. Here more organic derived. Dendrite, lot of advantages. This is what I meant by. You see here, electrolyte plays the same cathode, everything same. You go from this electrolyte. This is carbon dioxide evolved. Here it is reduced. It also, this is hard carbon cell, full cell. You see hydrogen? Hydrogen. Maybe the hard carbon we used is really bad. I don't know. It's not that bad. There are a lot of people who are using hard carbon worse than what I am showing here. So we need to completely understand. That's all I'm saying, and then do the right thing. Elimination of transition metal excepting lithium, that is sodium sulfur. I will have only one slide. You see the number here? Sulfur stores 10 times more charge than anything else I showed earlier. But voltage is half. But 5 times more capacity or energy density compared to the other cathode. But it has a lot of problems. Sulfur 8-membered ring, when the bond breaks, it forms Li2S8, Li2S6, dissolves in the electrolyte, it goes from here to here. Anode, creating a lot of problem. That is called polysulfide shuttling, chemical crossover. That's what we were talking about earlier when we were looking at the lab in NPL. Chemical crossover is a problem in any electrochemical system as long as you use a porous electrode, porous separator. So that's a challenge. And then you have to use lithium metal unless you use Li2S. So a lot of challenges that needs to be worked out. So sorry, I put the problems here. So how do we make good sulfide electrolyte? What electrolyte we use? There are so many things worked out. Right now, nobody has lithium sulfur cells with more than 300 cycles. You need 1000 cycles to sell it, and nobody has it. So that's the situation. Final aspect, elimination of mined metal. That's my dream technology. Sodium sulfur, voltage is lower, but grid storage is great. So it's a little bit more tedious than lithium sulfur, but if you understand lithium sulfur better, maybe we can make progress. So this may be way down the road, but we have to, as academic community, we have to think about tomorrow's problem rather than only considering today's problem. So work is, I just thought one slide I will show. So I'm not just talking, we are doing work in all those aspects I talked about. So this is my slide. This is important. Sometimes funding agencies may say you're supposed to do applied research. Yeah, I will do applied research, but I need to understand what I'm doing. Otherwise, I will go to the lab, either blow up or nothing will work. So what we have now is I showed you everything what I'm very humble to say, everything we use now was developed in 1980s. Graphite intercalation was done. I showed you 3 cathodes. They were all concept done in 1980s. That's what we use. 40 years later, what did we do? Chemistry did not change. Still the chemistry, unless we use lithium-sulfur or sodium-sulfur or something else, the other chemistry did not change. Same chemistry. What we did was engineering advancement, making the separator thinner, making the current collect thinner, making the electrode thicker, making the electrode better. That's all we have done from 1991 until to date. Newer chemistry, nobody is adopting. The problems are not solved. So if you do anything in your lab, don't promise, don't have a news release. It is going to change everything in 2 years. It will take 10, 20 years. So the one point I want to emphasize is basic science research is important. What we use now is all given, led us, that basic science research led us to these cathodes as well as the graphite anode. That's what we use. But we don't want to do basic science research just for the sake of basic science research. I mix this and that, whatever comes. I have a fancy publication in Nature or Science or Nature Energy and keep going. You can do that, but that's not what we want to do. Let us see what is the problem, and let's do that basic science to addressing that problem. I call it as use-inspired basic science research with targeted engineering metrics. Let me repeat it. Use-inspired basic science research with targeted engineering metrics. What I do in my lab is all chemistry. I did not change it. Whatever I learned chemistry, that's all I do. You still saw in my talk, but no problem. There is a lot of reception for what we do because it's addressing problem. It's trying to make things work better for the use. So that's important. Now, as we move forward, this will be the most important one. Everything I talked about, good, bad, with any of those materials, I had a slide I deleted. Electronic configuration, chemical bonding, chemical reactivity. These 3 things, that's it. Everything, cost, cyclability, everything can be explained. Or somebody behaving good, somebody behaving bad, everything can be related to these 3 fundamental things. That's what this is. So this will be the driver. Cost, sustainability, supply chain. High nickel, surface reactivity dominates compared to bulk. Polyanion, press density is more important because it's a low energy density system. Polymetric energy, that's why reluctant. If you can overcome that a little bit, that will be helpful. This has additional problem. Okay, also this LMFP, that blend also has some pulse power capability better than either the layered oxide or the LMFP alone. So that's another advantage. This is important. I mentioned already. Electrolyte plays a much more dominant role than generally thought. Your DG knows, we ignored, but that is the major thing. Those of you who work on batteries, don't forget about electrolyte. As I said, I will repeat it. Bad cathodes, bad anodes can be made to behave better, workable, if you have right electrolyte. And some of the things I don't want to say clearly, but I will say this. Some of the things will work for today, or we have today's problem, we have tomorrow's problem, we have day after tomorrow's problem. My talk covered all the way from today's problem, tomorrow's problem, day after tomorrow's problem. Some of the work people doing, they may say they are going to solve everything today. I don't want to say which technology it is. We don't want to hype. In my gut, I know some technology will not see anything for at least 20 years. Cell making, how are we going to make? If you have totally different thing, how are we going to cost effectively make cell? All those things we need to consider. So anyway, I will leave it there. So this is my current group. I'm grateful to a lot of people who have worked with me over the years. They are all over the world, about 300 people. Approximately 55 of them are faculty, all over the world, in the US, China, Korea, so many people. And I was lucky to have a lot of good people to working with me. It's very enjoyable to work with them. I'm very grateful to them. And more importantly, the funding agencies, US Department of Energy, funding our research consistently. That helps us to do whatever we want to do. Thank you very much. Yeah, of course, you can ask me any questions. I think I took long time probably. Yeah. No, you can, I am here. You can ask me any question. I have to go to the airport only at 7:30 p.m. So. Yes. How many of you work on batteries? Raise your hand. But I made initial few 10 slides. That should be helpful to you. That's why I arranged like that. The later ones I went fast.
Sir, actually, I found your presentation very, very inspiring. The main thing that we should all focus on, which we sometimes just deviate, is we have to work on basic research. Like we have to understand the basic things. We go on like building skyscrapers, but the foundation has to be very strong, and that is the main takeaway from your.
You are absolutely correct.
Yeah. Yes, sir.
That is what is needed. So I mentioned in the Calcutta conference as well. Because since you asked me, the education is very, very important. The industries are marching to make batteries here. They are going to employ a lot of young people. If those young people know the basic concept, basic fundamental understanding, physics and chemistry involved here, it will be speeded up. Speed will be very high. You can do faster. So that's very, very important. I hope everybody recognizes. I am a strong believer in educating people so that they have a good understanding before they go to the lab and do all kinds of things. Random things. Yeah, you can do random. Sometimes it will work. Many times it won't work. So you are absolutely correct. 110% correct. Yes.
Sir, I have a very different question. If at all I want to become a startup today, I'm not worried. No, simply I'm telling. I'm not worried that I should be a sustained startup for 3 decades, 4 decades. No problem if I want to make money, earn for next 1 decade. So what is the technology that I can take? Because during this 1 decade, when I'm earning money, slowly I will learn also what is the future. If at all I'm a believer, I may or may not be correct. If at all I believe like this, what is the advice you will give me? You can start like this so that at least next 10 years, you can make little money. So.
Okay. If I know exactly what I need to do, I won't be standing here. I'll be the next Bill Gates. But I can tell you something. I'm not ignoring the question. Okay. My goal right now is, yeah, money is good, but what can I do to the young people? How can I educate? The happiness I get is so many people work with me, then they go out, get good jobs, they're very happy. So many people all over the world. Okay, if I do that, I'm happy. Anyway, having said that, we have today's problem, tomorrow's problem, and day after tomorrow's problem. Right? For India, don't right away jump to work on tomorrow or day after tomorrow's problem. First thing what we need to do is try to make good cells with the chemistries already known. Develop confidence. Like I said, for example, LFP, LMFP. Oh, it's all already, everybody has done everything. How do I do a startup? I told you a very simple thing. Tap density. Think what is the problem? What can I do for that? The example I showed you is a good one. Tap density is a problem. Press density is a problem. Therefore, volumetric energy density is a problem. Do I make the material like everybody does, or I do it in a different way? There is another different way. By the way, that is patented. Okay, patented means patent not issued. So somebody is going to use it. There are people interested. We will see. So that is an example. So you do something like that, then you start up. You start your startup. Then you have something. You feel confident. Then there is a way to work. But I won't stop there. This is done. That example is done in my lab. It is one thing to do things in my lab. It is another thing to do in a startup. And it is yet another thing to do in a company like I will take your own company, Ola or Reliance or somebody. There are different levels. Whatever I did in my lab and showing, there may be scaling. Scaling is a totally different animal. We don't understand. If you make 100 gram, we can do it. You make 1 kilogram, you can do it. When you want to make tons and tons of material every day, there may be other challenges. We won't know. You have to be lucky. So there is different levels. So the bottom line, you have to come up something which is unique, and you know it is going to solve at least one small problem, then you go. That's the way I don't know whether I know what question you are asking. Do I work on LFP or LMFP or sodium ion?
It's a mind voice of many other lithium researchers. Yeah. Of course, I'm not having that one. Sir, actually, I have a question I'll tell you. Yeah. What is the stake of US today on nuclear batteries? Actually, this is a question I just wanted to listen from you. Because all of us, we started talking about nuclear batteries. What is it which is happening in the US?
So similar question came up. With respect to battery, what we work in the conference I heard, I was in a panel, my answer to them was, we cannot put all our eggs in one basket. And don't be afraid that there is only one first let me talk about batteries, then I will come back to your question. Similar question. It is not going to be one technology, one battery chemistry used all over the world. Different people need different things. In the Western world, people want or think to have long range, driving range, for example, is a different criterion. India, not quite so. Driving range is not the driving factor. Cost, sustainability is the most driving factor. Temperature tolerance is more driving factor because our guys go auto rickshaw, for example, hot weather, Delhi, cold weather, and things like that. So for that, LFP is better compared to layered oxide. Okay? So different parts of the world will use different chemistries. Some may only want to use sodium ion even though energy density is less. Some may want to use lithium ion with layered oxide because they want higher energy density. They don't worry too much about cost. You consider Western world, you consider Asia, some countries, you consider India, you consider African countries, you consider South American countries, different. So in my opinion, everything will have a place. The market is so huge, unimaginable. If you have something which is good in either in one of those aspects, you will have a market. Now, coming to your question. Do I do only one way, use solar energy, wind energy, store in the battery and then keep going? No. We should have our portfolio diversified. Nobody knows exactly how the cost competitiveness will be with every technology. Okay? Fuel cell has to be there, hydrogen has to be there, solar has to be there, wind has to be there, energy storage has to be there, nuclear has to be there. You have to diversify. That will be my answer. There is no one solution. And different people will, there is a safety concern with the nuclear, but you have so much software, so much technology improved, there may be warning, there may be this, that. I think they should be able to take care of. Do we do everything nuclear? My answer is no. You cannot have everything nuclear, no. But it has to be, everything has to be in the portfolio. We have to diversify. Yes.
So you're a very good teacher, I must say, right? So many of us sitting here, as ma'am said, we are not battery chemists, and people like me were never very good in inorganic chemistry. But today, after listening to your lecture, I can say at least the basics of battery is known to people like me. So thank you so much.
Thank you, appreciate it. That's why I say education is very important. Once somebody says you all the basic things, you will see how chemistry and physics is playing a role. People will automatically get interested. That's why I believe very strongly the education has to be good here. Teaching people, they should have in curriculum. There should be people teaching or some kind of a technology so good, YouTube or something has to happen. People have to understand, but there is no substitute for in-person classroom education. I'm not doing my class this week. I have 22 student graduate class. Some of the things I do here, that's I teach in my class. So I asked them, can I record the lecture, put it in the online? Raise your hand. There were 4 or 5 people we want in person. Okay, great. I like in person too. So I will have to have makeup class when I go back. So there is no substitute. I know this, but I teach 8 o'clock class. I thought they may not like 8 o'clock class, therefore they will tell me, put it online. They said, no, we want in person class. So the teaching has to happen in person. People have to understand the body language. So then it goes into the head. Zoom, it's okay, 50% may go, but there is another 50% it don't go. So.
Yes. Okay, thank you very much, sir, for a very nice presentation. I have a question on the initial slides when you talk about the energy consumption in different countries. So I don't see a direct correlation between the population and the energy consumption. US, it's like 0.34, but the energy consumption is 16%. So what are the driving factors actually for this?
Why they use more energy?
Consumption, when you show.
Because they are more industrialized. Lifestyle is different. In the US, one car, one person, for example, going all the way from here, from Dallas or Austin to Minnesota or somewhere, so many cars, Mm-hmm. So, and the economy, right? The more economy you have, you will use more energy. More industrialized, right? So that's what I mean. So I'm not diminishing anything. So we are in the growth. It will be going like that. That's why it's a warning. Train wreck is coming. So what do we do? That's what that slide is. We cannot ignore. It's energy is very, very critical for India. We have lot of opportunities to go. So,
thank you, sir.
Yeah, so don't ignore. Another one? Please photograph. Okay. Yeah, I'm okay. You ask me. That's what I do in my class. Let them ask questions. This is what I tell in my class. I don't know everything. I know only few things. If I know, I will say the answer. If you don't know, we will learn together. Same.